Hello my friends, welcome again to my video channel. Today we'll start a project which was not intended from my side. The HP8640B. My good old working horse since 15 or 20 years, I don't know exactly, suddenly said, no, I'm not your working horse any longer. It generated some smoke, typical electrical smell. The front panel got a little bit dark, no output. Then it came back to life. Then it went again off, a ticking sound. So I decided to open it, and now you see the counter in the background, the HP5640, which is normally resting above this generator, is now a lonesome rider. So let's do something against this. I opened the generator on the bottom side and I switched it on again. I saw a little bit of flashlight and the smoke was generated here on this pin. You see this pin here? It was burned, generated smoke. I removed the solder and then I saw it had not a good contact. Obviously the solder was burned. The wire inside or whatever it is was also burned. Looked overloaded or corroded. Don't know. What is this? Well, we are here on the power supply part of the generator. This is a power transformer, primary side, secondary side output. Here we have the connector to the rectifier board, filter caps, and here we have the voltage regulators. We can look at it from the other side. It's a power transformer. The rectifier board I've already taken out to check it, whether we have a problem here. These are the filter caps, and here we have the power regulator, 20 volt plus minus 44 and 5 volt. Here we have the minus 5 volt for the fan drive. The fan has its own driver. Obviously we have a problem in the power supply. My first check will be, of course, the diodes, whether they are still okay. But anyhow, whatever the result is, we have to solve this problem. I cannot resolve it again simply because it's too badly destroyed. It's corroded. So if you have to take out all the whole transformer, unsolder it here, shift it out, and then resolder the pins again. We will see it in the schematic what we are talking about. This is a part of the schematic of the main board. This is a rectifier assembly. This connector is this one here. Pin 1 is pin 1. And this where we have the damaged connector. It's pin 19. It's this side here, pin 19. And on the transformer side it's T1, pin number 10. This is pin number 10. So when you look into the schematic, what is pin number 10? Where do we have it? We have it here. The documentation is good, but it's always a lot of paper. That is pin number 10. And 9 is the other side, and here we have the rectifier part, the cap, and this pin here is, or better said, this pin on this side, not 19 on this side. This pin is okay, damaged. So that's a problem. We have to take out the transformer to repair it. But of course we have to check these diodes, especially these diodes, whether they are shorted, or the electrolytic cap, or something in the voltage regulator. This makes us see 44 volt. Maybe we have here a problem, or a short in the load. Anywhere else. So let's start first to check these diodes, but first I will take out the transformer. To take out the transformer we have to remove these two screws, big and fat screws. These screws are already loose. There was a cap plastic cap covering the primary side. Safety measure. We have to unwire these, unsolder them to the primary side with the tapping for the various voltages. And then we have to unsolder these connectors, this row and this row. Not this row, this is a plug for the rectifier board, only this one. There's another solder connection which does not look very good. It's a blob. Blob is always dangerous. Here also we have a spot inside. So I think it's not a bad idea to resolder everything. But first, of course, we have to take out the transformer. And I see now these connectors, these pins are not all very well soldered. They are all too short. A little bit too short. The primary wires are also unsoldered. Always make a note which wire is where. And then I think it should be possible to push out the transformer when we remove these two screws. Well, this unit is sealed completely. Welded, as I assume. Yes, it looks like welded. I assume filled with some resin or so, whatever it is. 1079, okay. It's from October 1979. There have been flashes, sparkles in all directions. Can you see it? When I change the light in one position, you can see something, but it looks like the problem is outside the transformer, not inside. I cannot open it. It is obviously also sealed or glued or whatever, but this indicates clearly that we have the problem outside in the contact and here in the pin, this pin which made the trouble. So we have to clean it and then carefully to resolder it. Maybe I will feed in a piece of wire and make a bridge or so. I make a short DC measurement to the secondary of this winding, and I measure, what does it say, 2.6 ohms. Yes. So I can say the winding itself is correct, also the pin inside. So we have only a problem here on the surface. And here a look onto the power supply main board from the other side, where the transformer is fed in here. And it's obvious which contact had a problem. I have to clean it also on this side. Not nice, but again, I hope it's only on the side of the outside of the transformer. The ohm measurement shows me a good result, and so I think also the diodes will be okay. It was really only a bad solder connection which degraded over the years, got a little bit hot, degraded more, and then we had a runaway effect, and suddenly the solder connection was too bad for operation and generated such sparkles. An outside short circuit I think wouldn't do it. It would cause a sudden shutdown or so. But of course I have to check it. But first I will clean this one. It's necessary now to clean all the pins. I use a cutter or so from all sides to scratch off any oxidation, corrosion and so on. And then resolder them, because we have the problem here that these connections of these pins here are vias, so it's necessary to solder it also inside the vias and not only to connect it on the top with a blob. And here, that's what obviously happened here. We have the pin coming through, and then it was soldered only on the top, because obviously the soldering iron was a little bit too weak, or the guy or the woman who did it was a little bit too fast. It was a contact which is good enough to pass through the quality check in the factory, but over the years this connection gets weak, so we now have to look when we resolder it again that the solder really drops or is sucked into the hole completely, because I've seen when I unsoldered it with my desoldering gun, it was very easy. So there was only some connections on the top, which is not good. And now I will solder all pins step by step. Sorry, some more solder. The transformer is in, fixed with 4 screws, as it was before. When we squeeze down this main board completely, then we have a little bit more overhead and more length of the pins. So maybe it was also a problem that the board was not totally bent down. Now it is. And I will flip it around by 90 degrees and then solder it so the solder can suck into it. And here at this pin, it was where it was damaged, I will feed in some wire, some millimeters, and connect it here to the pin, because I don't know what happened to the trace here. It looks a little bit burned or damaged, I'm not sure. So I will make a connection directly from this pin to this pin. Here you can see what I mean. I fed in a appropriate wire with a plier, squeeze it down into the hole, and then I can solder it, because I see this pad is loose. It's not stable, so we need a direct connection from the pin to the transformer to here. When soldering such pins, it's important that the solder is sucked into the hole. So use a big iron. Okay. So it's always an advantage that the pins of the transformer are tinned before soldering finally. And last but not least, do not forget to solder this wire to the pin on this side. Now I will clean it a little bit, and then this topic is solved, and the next problem is now to check the diodes, whether they are still okay. The diodes which are connected here on this board, whether the short was really under the problem here, or short, it was not a short, the interruption, or whether we have really a short in the diodes or in the subsequent electrolytic capacitor. It is C3, this one, this big unit. What is a good and what is a bad solder connection? I'm sure you know it, and the guys who should learn it don't watch these videos. This is a good one, when the solder is very tight to the wire and to the board. In this shape, and this is a blob, which is always dangerous, or it is one big blob, or some ring around or so. We don't know what happens here. Is it really a contact, or is it only flux? So the blob is swimming on the flux, or it is fixed only here and not here, or vice versa. Such connections are always in doubt, and whenever you see such a round connection, such a blob, then it's always dangerous. Remove the solder and look what happens. Clean the wire, clean the board, and look that you can solder it this way. And I have forgotten to mention, when we have a via, it's necessary that the solder is sucked into the via on both sides, if possible, but at least on one side, to have good contact not only on top of the layer or bottom of the layer, also in the via itself, for good contact. And that was obviously the problem we had here, that we had more or less contact only on the top, like this, but not here. And this requires a good iron, which makes not only heat for the wire, also makes heat for the board and for the via, because vias are heat consuming. Now I do the check on the rectifier board. The 4 diodes in question, which supply the output of the power transformer, where we had the faulty or the interrupted connection, which could have been caused by an overload or a short circuit. These are these 4 diodes. I will check them with my these 4 are here. And you see my component tester. It's very nice. I can check them in the circuit because the transformer is not connected, so we have no DC bypass. This is the first one. Okay, it's reversed, and this one, and this one. All these 4 diodes are okay, and while we are just on this trip, I will check also the other ones. This one, this one. Where's one? This. This. Okay. And this, and so on and so on. But I found one diode. So this is okay. And this one is not okay. You see? Here is a faulty diode. The other one in the bridge rectifiers are okay. The other 3 ones are good. Only this one is not okay. And this is this one. But it has nothing to do with the circuit in question. This is a rectifier for the fan. And there's one diode not working. Let's have a look into the schematic. The faulty diode is CR17, this one. And CR17 is this one. This is a part of the circuit AB on sheet 23. And sheet AB, connection AB on sheet 23. This is 23. You can see it. This is a fan circuit. Sorry. This is a fan regulator. 23 AB. And this means that AB does not get a fully bridge rectified AC. It gets only a half wave rectified signal because the diode was interrupted. But I think the capacitor is big enough, so there is no problem with the fan. The fan will run anyhow. But this diode has to be replaced by a new one. I have to look into the data sheet. The original diode has a rating of 400 volt and 1.5 amp. I assume the 1.5 amp is a continuous current, DC rectified or RMS current. I have here a bag with diodes from my high voltage project with the high voltage power supply. So I have 1000 volt. These are the P1000M. And the data sheet, we have it here, says a current of 10 amp. The 4 new diodes in place, they are checked, they are okay. And the old ones, all 4 have to go. One is bad, of course, the other 3 I don't know how they survived this asymmetrical operation over the years, decades. I don't know how long it lasted, so I will throw them away. It's a best way. When I wouldn't have had the problem with the transformer, with the connection, it may be a short on the board. I have not examined everything. I would never have detected it. It's crazy. But the filter capacitor is so high, so big, that the asymmetrical operation of the bridge rectifier, I think, didn't affect the fan. Maybe I will see that the fan runs a little bit smoother now. I'm not convinced. But okay. Now we have to check the electrolytic capacitor. Yes, it was sufficient to open the 2 screws. Then we can take it out. What does it have? 3900 microfarad. 75 volt DC. Okay, I will check it in different ways. First I measure the capacity alone, without a voltage check, only the capacity and the quality. 3.49 should have 3.9 millifarad. or 3480 microfarad, should have 3900, so a little bit less at 120 Hertz. The problem is when I measure with a higher frequency with 1 kilohertz, and that's what we can expect from such a big capacitor. The inductivity plays a role. Important is the quality, D, or when I switch to the quality it is 6.7. I think that's okay. There's no sign of any leakage or any blow up or so, nothing. I will do a short test with the isolation with the ohm meter, whether we have a problem, but if we would have a short circuit which would cause the damage we had, then we couldn't measure a capacity. I'm measuring here the DC resistance in the range times 1000 kilo ohm. That means times 1 meg ohm. We are in the range beyond 100 meg ohm, between 100 and 500 meg ohm. When I unplug it, okay, it goes to 500 meg ohm or infinite, and so we are in the range of, let me say, I think 200 meg ohm or so, constant. So I can say this capacitor is okay and it has no short. That's important. So the problem, whatever it was not this capacitor. It's a good moment now to clean this part of the compartment because there's a lot of dust. Here's a fan. Maybe I can clean it also a little bit. Here is one of these reefer caps. Just see. The lower side, it's a little bit. You see? The lower side, the reefer cap is broken. It has blown out. Next topic. When we open a case, we will find a lot of trouble. Yes, really. I found a capacitor. This one had 22 nanofarad. It's a Y capacitor, okay. And the voltage was 250 volt AC. Hey, gentlemen, we have 230 volt AC now. Nominal. And they built in 250 volt in a 230 volt system. Okay, we had 220 volt in the past, but this one has 22 nanofarad, 1000 volt DC. This is also good for 250 volt AC. For example, here we have one 47 nanofarad, 2000 volt DC equals 700 volt AC, or 1000 volt is 350 volt AC. I think that's okay. I will take it. And the new reefer cap, which is not a reefer cap, is in place. The electrolytic cap also checked good. I don't have still the board, the rectifier board in place. I will first check the output of the transformer. I will switch the unit on, and then we can measure here the voltages, but they are not rectified. And my last project. Now I can use it simply for testing the AC voltages, the output. I don't have a real T1 specification which winding supplies which AC voltage, but for example this first one which we have repaired supplies 40 volt DC, so we have 50 volt AC. That's obviously okay. And the next one, 8017, this is 20 volt DC. When we have 20 volt DC, we should also have 20 volt. There's a little bit. We have 25 volt AC. That's okay. The next one is 1615. This is 5 volt output. Okay. We have 12 volt AC. 1413. This is the Supply for the fan should also be in this range. Yes. Ten, 13 volt. Same voltage. And the last one, it's again 25. And this one also supplies 20 volt, positive 20 volt. So the output voltage of the transformer is now logical, realistic. But first I should check the fuse on this board. I've seen in the schematic there's a fuse in it. So I will take it out. Look for the fuse where it is. There are two fuses, 1 amp and 3 amp. I will check them. They're okay. No signs of a short circuit, no damage, no burnt components. So I can reinsert it. I decided to start the generator with my Variac. Now I have 115 volt with 230 volt. Nothing happens. Frequency can be set. Fine tuning. Okay, the fan rotates as before, no difference. Well, I think that's it. Problem is solved. There was one problem with the contact in the power transformer, as we have seen, badly burned. And we had 2 windfall profits, 1 bad rectifier diode for the fan supply, and the reefer cap. I hope that's all in this generator, and now I can take it back to service. And my frequency counter is not a lonesome rider any longer. He has his companion back. That's the end of this project. Not planned, not intended, but I was forced to do it. It was easy, as we have seen, no big problem. The fault itself was only caused by a bad contact. I show it to you. If you have such a generator, look at the solder connections of the power transformer. Maybe you have the same problem as I have, and up to now, when you had no problems with it, maybe you have the problem tomorrow, to prevent any fault. Then second, look at the reefer cap. These reefer caps are always bad. And the other windfall profit was a bad diode in the rectifier for the fan. Well, that's it. Stay healthy, stay tuned, and see you on this channel.